Good morning. Welcome to this session of Black Hat. This talk is next generation of exploit kit detection by building simulated obfuscators. You are in Mandalay, BCD. The speakers today are Tongbo Luo and Xing Jin. Before we begin, there are a couple of announcements and notes to take. We want to make sure that you stop by the business hall, which is located downstairs in Bayside AB. The Black Hat Arsenal is on the Palm Foyer upstairs on level 3. And of course, there is the Arsenal reception this afternoon or evening at 5 p.m. If you haven't picked up your merchandise yet from the Black Hat swag store and bookstore, this will be your last chance to visit that today. So please feel free to make your way up there. And also visit the Kali Linux lab upstairs in Mandalay Bay A, which is just down the hall. Thanks you for putting your phones on vibrate for us. We really appreciate that. And without any further ado, I present your speakers. Thank you very much.
Hi, everyone. Thanks for coming to our session. And my name is Tongbo, and this is my colleague Xing. And we are going to present our project, next generation of exploit kit detection by building simulated obfuscators. A little bit of background of ourselves. We are security researcher at Palo Alto Networks, and our research field focus on cybersecurity, mobile security, and we also do some funding things to explore some vulnerabilities. In this presentation, we will start with the background and the motivation, and Xing will talk about the challenges we are facing during the project. Then I will talk about our generic approach to solve the problem, and the last is some result and observation we want to share with you. And Xing will talk about the first part of the presentation.
In our work, we built a website, jsdarwin.com, which can do similarity-based detection on malicious exploit kit JavaScript. The users only need to upload a file or URL. The website will check it with existing exploit kit families and show the result. As we all know, the similarity-based detection requires a large sample set. The detection rate depends on the number of samples collected. However, exploit kit may apply various of techniques to prevent the researchers and engineers from getting a large sample set. So we want to rebuild the obfuscator, which can be eventually be used to boost a large sample set. Here is what an obfuscated page looks like. It usually consists 3 parts: the encoded payload, unpacker, and eval trigger. The encoded payload is generated by the encoder of obfuscator, and the input is original malicious payload. The other 2 parts is generated by the obfuscation engine of obfuscator, and their input are unpacker template and eval template, which are also provided by the obfuscator. Previous researchers most focused on the obfuscate page, which is the output. While our work wants to start a new angle, we want to focus on the obfuscator. We want to rebuild the obfuscator in order to reconstruct the encoder, identify the template from obfuscate page, also reproduce the engine logic of obfuscation engine. This picture shows the first layer of the obfuscation. There may be several layers of obfuscator in obfuscation. We only tackle the first levels. However, our techniques can be applied to different levels. Here's a quick example of obfuscator reverse engineering. We have 3 simple lines of code here. You can see there are 2 ways to construct the eval string here. The first two, they are using the string concatenation to construct eval string. And the third one, it used the substring method. The way they used here, we call it obfuscation engine logic. The first two, they are using the same obfuscation engine logic. So we say they belong to the same variant. Furthermore, these three lines of code can derive the same eval template, window, eval string, and the payload. The eval string is constructed by the obfuscation engine logic. And this template, they are sharing the same template. So we say these three lines of code, they belong to the same obfuscator version. In the real world, it isn't easy to derive a template. The first challenge is the code complexity. In the real world, the obfuscated page usually looks like this: hundreds of lines of code with a lot of random variables. It's very hard to tell which part is generated by the template and which part is generated by the obfuscation engine. The second challenge is the data complexity. We have a large big data set, 20,000 samples over 2 years period. Also, at the same time, we may have different versions and variants mixed together. Data complexity makes our work harder. Now, I will let my partner Tongbo talk about the details of our approach and how we deal with these challenges.
Okay, this figure shows the high-level picture of our approach, giving a large sample set, which can be generated by different obfuscator version or variant during 2 years. We first leverage JavaScript normalization to extract the structure of the script from the sample, and then we utilize hierarchical classing model to group a sample in a way that samples from the same cluster are generated by the same obfuscator version or variant. Then we just need to manually analyze samples within each cluster to reproduce the obfuscator to figure out what the original obfuscator looks like. So the first step is the JavaScript normalization. It involves 2 steps. First, giving this piece of JavaScript code. Then we tokenize it into a series of JavaScript tokens. And then for each type of JavaScript token, we map it to a unique character. Then we put all of the characters together to construct the normalized script from the source code. Basically, the rationale behind the normalization is to ignore the superficial obfuscation techniques, such as randomize the variable name. The different randomized name, variable name can be mapped to the same character after normalization. You can also tell that from this example, the normalized script is more like the structure of the code. So later we will do some similarity comparison in terms of samples structure. After normalization, we found out that the number of unique normalized script is significantly reduced. For example, among the 7,800 Angular samples we have collected, we only identified 613 unique normalized script, which means the rest of them are just share the same code structure but fill some randomized variable name or some garbage data. And the same situation happened to other exploit families as well. And for example, if these 2 pieces of JavaScript code, they are different in their source code level, but they are completely but they are different in the source code. But after normalization, they are identical. We further analyze that why so much number of samples have the same code structure. So we further analyze them. We found out that the majority of the samples, they are collected at the same day or apart 1 or 2 days. For example, for the Angular samples we collected, and for the samples that have the same code structure, the 36% of samples are collected the same day, and the 24 are collected apart 1 day. And I want to use this figure to tell people who work on the exploit kit although you will see the majority of the samples are different at the source code level, but don't panic when you analyze them, because of the majority of them are just share the same code structure. So all you need to do is just to figure out the one of them, and you can understand all of them. And this can also tell the people who are trying to collect the samples on the Explore kit on their landing page, how often do you need to update your sample set to get more data. And also we try to figure out whether we are trying to repeatedly collecting the sample from the same server. Actually, it's not. The more than 80% of the samples we collected, they're from the different domain and the different IPs. So we are not collecting the samples repeatedly from the same server and cause this issue. Back to our approach, and we know how to extract the structure from the script. The next, so now we narrow down the number of samples we need to analyze this, but it's still too large, and we have to find a way to cluster samples based on their obfuscator version or variant. And we have observation that the obfuscator evolved not from the scratch. It only developed a new obfuscator. It normally just modified the previous version and did some modification either on the engine or on the template, and to construct a new obfuscator variant. And based on this observation, we have assumption that the more similar of two samples in terms of their structure, the more likely that they are generated by the same obfuscator version or variant. And how to define the similarity between two samples in terms of their structure, we just first need to calculate the ID distance on the normalized script, and then derive the similarity score based on the ID distance using the following formula. Basically, the similarity score will be between 0 and 1. 0 means that the samples are completely different. 1 means that they are identical. We know how to compare the similarity between two samples in terms of their structure. The next question is how to cluster them. There are two mainstream clustering models, hierarchical model and flat model. Flat model, which is popular with its algorithm k-means, which is quite popular. I think most of you guys have already learned that in your daily work. It is quite easy and efficient, but it has some drawbacks. One of the drawbacks is that it requires a predefined k as a value as an input. And this k is the number of clusters that you want to group the sample into. In our case, the k can be interpreted as the number of obfuscator version or variant we want to identify, which is hard to predict because when we collect the samples, we don't have those information. And even though we can measure the k using some ways, it still doesn't work because obviously new version or new variant will come up later. Therefore, we choose to use hierarchical clustering model. For the hierarchical clustering model, we just need to build a dendrogram based on the similarity of the samples, and then for each the dendrogram is more like a tree, and each node in the tree is a sample. And the structure of the tree is arrangement of the samples. Then we just need to find a threshold to cut the tree into subtrees, and each subtree is a cluster. The problem is that how to find this best threshold to cut the tree. And we just pre-select 50 pair of samples and mark them whether they are come from the same obfuscator version or variant. And then we run our algorithm on all of the samples we have collected, including those marked ones. We build a dendrogram. Then we need to just adjust the threshold to find the best place that can cluster the marked samples into the correct the cluster. Based on our evaluation, we believe that the identifier to identify obfuscator version, the threshold should be between 0.4 and 0.5, and to identify obfuscator variant, the threshold should be between 0.85 and 78 and 85. the major difference between this threshold and the K is that the threshold won't change in the future because it reflects the nature of how the obfuscator evolves, like how many percentage of the impact that the obfuscator will introduce to the page. From the previous two steps, we know that we can group the sample in a way that samples from the same cluster are generated by the same obfuscator version or variant. The final step is to analyze the samples within each cluster. Our approach is that we just look into their normalized script like this one, and then we do the alignment on the normalized script. Then from the alignment result, there is some matched part, which is a common part for all of the samples, and they are in the right part, and there's some gap in the alignment result, which is in the green part. Then we just for the matched part, which is 80% of the samples, because we use the threshold 0.8 to do the cluster, and we just need to write a script to look back to their original value to see whether it's a hard-coded value in the template or it's a randomized value in the template. But for the gap part, they are most likely generated by the obfuscator engine. And since they are just less than 20% of the samples, it is now hard to figure out what the obfuscator engine looks like. So by iteratively repeating this approach to all of the clusters, we can easily reproduce all of the obfuscators, each obfuscator variant. Then we just run those obfuscator, and it can generate more samples than we collected. But by more sample, I mean the more code structure, and we can easily boost our sample size 3 times. And since we are using the similarity-based approach, the larger sample size means higher detection rate, and we also increase our detection rate as well. And the third benefit of this research is that we are trying to look into how the obfuscator evolves. So we also do some research on how the evolution of obfuscator used by the Obfuscate. I hope that if you are working on the Obfuscate-related research, you can get some insights from our new angle.
To better understanding the exploit kit obfuscator, we also draw the timeline of obfuscator life cycles for each exploit kit families. This is the first work people tries to use the obfuscator life cycle to represent the evolution of exploit kit family. This figure shows the life cycle of nuclear obfuscator over 2 years period. Each line represents an obfuscator version, and each block in the line represents an obfuscator variant. According to one report, on December 2014, a new version of nuclear exploit kit emerged, and which totally replaced the old versions. Also, from our timeline chart, we can see the same result. A new version is deployed on December 2014 and totally replaced the old versions. The insight of the nuclear exploit kit obfuscator we can see here is a new version is deployed after the old version is dead. However, things are quite different for the Angular exploit kit. We can see the Angular exploit kit is extremely prevalent. The version 1, it lasts for 2 years, and Angular exploit kit is very complicated, and it applies aggressive tactics for evading detections. Because each version is complicated, so they don't need to change a lot for each versions. So there are only few obfuscator versions and variants for the Angular exploit kit. We also did some investigations on the domains deployed on each versions. We want to see how many domains are affected by the angular exploit kit in our samples. And here's the numbers. For detailed information, you can look at our papers. At last, we want to see how the obfuscation engine changes affect the variants. First, we will see the variant nearby. We check the variant 1 and the variant 2, their similarity. It's about 0.8. And similar things happen to variant 2 to variant 3 and variant 3 to variant 4. We want to take one step further. We want to see what's the difference between the variant 1 and the variant 3. If the obfuscated engine logic change at the same place, because each one change 20%, if they are changing the same place, the difference still should hold at 0.8. But however, the truth, it dropped to 0.67, which means the change on the obfuscated engine logic happened at different places. The similar things happened to variant 2 and variant 4. Finally, we check variant 1 and variant 4. We can see the similarity dropped to 0.47. With previous research, it's hard to link the variant 1 and the variant 4 because their similarity dropped to lower than 0.5. But with our method, we can apply threshold to link the variant 1 and the variant 4 together and also make the link. And this is the advantage of our work.
Okay, before the end of this presentation, I hope you can learn the following 3 things from our presentation. A new angle to explore kit by looking back from the obfuscator page to the obfuscator, and the generic approach that can boost the sample set and improve the detection rate by reproducing the obfuscator. And then we also show the evolution of obfuscators used by the exploit kit in the wild. If you are working on the same field, I hope you can get more insight from this new angle. And at last, before the Q&A part, that we also open source our code, and you can download them from the GitHub. And if you have any questions, and you can shoot us email, and you have any suggestions or new ideas on this, please contact us. And again, thank you for your coming to this session. Thanks.